Welcome back, everyone, to the Wilson Science and Technology Forum. Today, I'm happy to introduce, I guess I should say, a fellow Nittany Lion, John Morrow, who is I'm a Penn State alum, and John is the department head in material science and engineering at Penn State. John, it's great to have you with us. We're going to hear today about glass, which is historically one of the oldest constructional materials we have ever used. However, it continues to evolve in our contemporary world because of the work of guys like, and especially gentlemen like John Morrow. John has a remarkable career both not only at Penn State, but at Corning. And he's been a developer, an inventor, an entrepreneur, and someone I'm just delighted to have with us today to speak about glass for a sustainable future. So, John, I'm going to turn the floor over to you and welcome to the Wilson Forum.
All right. Thank you so much, Ron, both for the invitation and for your very kind introduction. And thanks to everyone for joining me today. So, the title of my talk today is Glass for a Sustainable Future. I would like to give you kind of an introduction to the importance of glass historically and bringing modern civilization to where it is. Also, take a glimpse into the future at some of the possibilities that lay ahead. I want to tell you a little bit about my own personal journey in glass, and including some of the things that we're doing here at Penn State, especially a new project that we are working on called Line Glass, which is meant to be a replacement for just standard everyday glass products that dramatically lowers the carbon footprint of glass manufacturing. So with that, I will get into it. Um, Great. So glass is often a material that we don't think too much about because it is something that we look through rather than look at. And I was really delighted a few years ago in 2018 when The Atlantic published this article calling glass humankind's most important material, saying glass has changed the world like no other substance, but people usually overlook it. And more recently, just 2 years ago in 2024, the cover of National Geographic declared this to be the glass age. And they made the case about how cutting edge glass technology is helping reshape this ancient material for our future. And I think when people think about glass, there is a tendency to think about it as an old material because people have been making glass for thousands of years. But if you look at the glass around you and see all the ways that it has helped to facilitate modern civilization, there's so many different aspects of glass that touch our lives every day. One of the most basic is glass windows for architecture, whether it is homes or office buildings. This is a material that is able to let in the outside light while providing a good thermal barrier between the inside and the outside. Also, good corrosion resistance against water and acid rain. And it does this, very cheaply and over many decades without, any issues. There's also glass lenses that were invented hundreds of years ago. I think most of us are wearing corrective lenses of some sort, and glass technology was key to making that possible. There's also the glass lenses that are used in the tools of scientific discovery. Before the invention of glass lenses for telescopes, astronomy was just done by the naked eye. And with the invention of telescopes made possible by glass technology, that was a huge step forward for the entire field of astronomy. Glass lenses for microscopes was essential for the development of microbiology and the discovery of microorganisms, showing that there's this whole world of unicellular life out there, and how that they were responsible for diseases and the whole field of epidemiology. This all was made possible by glass. Glass containers are used for beverages and food packaging and also for medicine. So if you've had any vaccine recently, that was probably being contained in a glass vial that was designed to have very high chemical corrosion resistance and high mechanical strength to make sure that the vaccine is viable and not contaminated. Right now, we are conducting this lecture by sending signals, optical signals, over very thin strands of glass called optical fiber. Each strand of glass is about the same thickness as a human hair, and it is made out of the highest purity fused silica that has ever been invented by humankind. The entire world is connected by these thin strands of glass. This was what enabled the information age. So every time you're using the internet, you are sending information optically through these thin strands of glass. And it's not enough to be able to transmit that information. We need to be able to see the information as well. And all of the displays that we're looking at now are highly engineered on glass substrates. And these glasses are designed so that they don't interact with the thin film transistor semiconductors that are used for each of the individual pixels. Whether it's the old cathode ray tube displays, like the old monitors and TVs, or the new flat panel displays, these were all made possible by advances in glass science and technology. And then there's these computers that we carry around in our pockets. And one of these smartphones is more powerful than the most powerful supercomputer from a couple of decades ago. And the glass on the cover of this is Corning Gorilla Glass. And this was designed to have very high mechanical strength and also the right electrical properties to transmit the tiny electrical signal from your fingertip to the computer. And what I think is especially interesting about these devices is that glass is no longer just something that you're looking through on the screen, but it is also now the primary means by which you interface with the device. So when you are interacting with your smartphone, you are doing so using your fingers through a piece of glass. Um, Going forward, we also have the use of glass in transportation, whether it is cars, trains, planes. We need to be able to see out from our vehicles so we can drive safely and at the same time be protected from incoming stones or other flying objects. So these are just some of the many ways that glass has brought us to where we are as a civilization. And looking forward, we are really just beginning here, this glass age. If we look forward in information technology, there are new flexible, even foldable displays that are being made now with ultra thin sheets of glass or displays being built on polymers using glass as a substrate, like a carrier for building the displays. When you make glass as thin as, say, 50 microns or so, it actually does become very flexible. And so you can have these foldable, flexible displays. High refractive index glass lenses are a key component for augmented reality glasses. So this is enables you to kind of superimpose images on top of your reality to get additional information. Glass is also being used as a medium for memory storage. This particular image comes from IBM. There was just a big announcement from Microsoft that they are doing the same thing. They are using silica and encoding information in 3 dimensions into glass. And the information stored, it can be done 3 dimensionally instead of 2 dimensionally, like with conventional memory storage. And also, it lasts for many orders of magnitude longer in time compared to traditional magnetic memory storage. The next generation optical fibers are also going to be key for quantum communication. And when you've got entangled photons, you need to have extremely low loss. So, lots of great opportunities ahead in information technology. Likewise, in transportation and architecture. One of the big trends in automobiles now is going towards self-driving cars. And that means we're going to have more screens on the interiors of your cars with more information, more infotainment. Also, there will be new windshields developed to go to lighter weight, stronger glass used as windshields. Windshield technology has not changed since like the 1960s, and it's still much heavier than it needs to be. And one of the ways that you can go to more fuel efficient vehicles is to go to lighter weight vehicles, and improving the glass technology is one way to do that. On the architecture side, going to more energy efficient buildings, one of the new technologies is vacuum insulated glazing, where if you've got a double pane window, instead of having a noble gas in between the two panes, you actually pull a vacuum. And so that decreases the amount of heat transfer that you get, but it also creates a mechanical stress. And so this is made possible by improving the fatigue behavior of glass to make sure that it can withstand those stresses over many decades. There's also new glass technologies being used for modern design and functionality, whether it is the Shard in London, this glass bridge that you can walk over the Grand Canyon if you are brave enough, glasses that are being used to help enable internet connectivity in devices and appliances around your house, and also acoustic damping glasses to help attenuate sound. When it comes to energy, glass plays a really key role in enabling the next generation of renewable energy. So windmill turbines, they become more efficient with larger turbines, and these are fiberglass reinforced composites. And so in order to enable more efficient wind energy generation, new generations of fiberglass need to be developed with higher values of Young's modulus to get higher stiffnesses to enable these larger turbines. So companies like Owens Corning are investing a lot in these next generation fiberglass technologies for wind energy. Then there is solar energy generation. Glasses are used as substrates for photovoltaics. Actually, we just installed a bunch of panels on our house, and so we are making good use of those as well. There's also glass technologies for solar thermal energy, where you've got parabolic mirrors that focus light on this glass tube that have a polymer inside that converts to a liquid when it is heated up from the solar radiation. So this converts the solar energy into thermal energy and then into electricity. Then there's also glass tubing that is used for photobioreactors, where we take advantage of the natural photosynthesis process to convert solar energy into chemical energy. So there's all kinds of ways that glass is helping to enable this next generation of clean energy generation. And glasses are also used for energy storage. So John Goodenough, who unfortunately passed away recently, he was, very active in the lab up until his final year, and he was inventing new glass-based technologies for next generation batteries that would go beyond his Nobel Prize winning invention and offer higher density energy storage, safer energy storage, and greater cyclability. Then there's glasses for healthcare. Glasses are used for vaccines. They're used for medicines. So EpiPen, this is from a company that my advisor has. So out of Alfred University, he's got a company that does ion exchange strengthening of glass, and this is used for patients who have like bee allergies or other allergies. And this glass needs to be able to withstand high stresses, so patients can inject themselves with life-saving medicine if needed. Then there are glasses that have silver ion exchange into the surfaces, and silver is a known antimicrobial agent, and this helps to prevent the spread of diseases, like if you've got shared touch screens that are used in hospitals or ATMs. And then there are bioactive glasses that actually get embedded in the body. So some of the early ones developed by Larry Hench and then Mohammed Rahamad are used for helping to stimulate natural bone tissue repair and tooth repair. And more recently, Steve Young and Delbert Day, Dell's also a Penn State grad, um, so now at Missouri, they have developed glass fibers that are being used to help enable soft tissue repair. This is useful especially for diabetic patients, many of whom have open ulcers that just do not heal for many months. And these ulcers can be as deep as going down to the bone. And with this new glass fiber technology, these glass fibers get packed into the ulcers. They dissolve over the course of a few days. The fibrous microstructure helps to stimulate the body's natural healing process. And as the fibers dissolve, they deliver the chemicals that the body needs to heal itself while also maintaining an antimicrobial environment. Um, Now, as scientists and engineers, we tend to think about materials in terms of, what are the useful things they can do for us from an engineering perspective. And it's often easy and unfortunate to overlook the impact that they have on our society through their culture and through their use as an artistic medium. Glass has been a favorite artistic medium for humankind for thousands of years, dating back to glass beads in Egypt and Mesopotamia. What we're looking at here are the beautiful, famous stained glass windows from Sainte-Chapelle in Paris. So these are about 900 years old, and glass was chosen by King Louis, so better known as Saint Louis now, as the medium for building this beautiful chapel that was meant to house the crown of thorns from Jesus. So King Louis had purchased the crown of thorns from the Eastern Roman Empire in Constantinople when they were in trouble, and he transferred them to France, and then he built this chapel to house them. And each one of these beautiful stained glass windows is telling a very detailed story from one of the books of the Bible. And so if you go inside Sainte-Chapelle, it's like being inside this beautiful work of art with so much detail, so much color, and the natural sunlight coming in just has this wonderful effect. Why was glass chosen as the medium? It is because of its engineering properties, right? It's high corrosion resistance, high optical transparency, the ability to get so many different colors based on the different dopants that are used, its good mechanical strength, the ability for it to take on different shapes, the ability for it to last for hundreds of years. But also, it's just such a beautiful material. And all of these things come together, and now we can go to Paris and enjoy this beautiful work of art just as it was 900 years ago. So, for all of these reasons, I was actually part of an international effort to petition the United Nations to declare 2022 as the International Year of Glass. And this was approved by the UN General Assembly. And we're very honored that the very first international year from the United Nations that was devoted to a material was devoted to glass. So we had a year-long set of activities. Now, switching to my own personal journey in glass, I first fell in love with glass when my parents took me to the Corning Museum of Glass when I was just a young kid, and I wanted to see every single piece of glass in the museum. And you will know if you've been there that that is a lot of glass. It would take a very long time, but I loved how beautiful it was. I loved watching the flame workers and the glass blowers and seeing all the different shapes and the colors that glass could take on. I didn't realize that glass was a valid career choice until I saw this VHS video from a professor from Alfred University, Dr. Alexis Clare. And she had this kind of Bill Nye the Science Guy type of video about glass and ceramics and all the cool things that they could do. And when I saw that video, I was like, wow, I want to study glass. I want to go to Alfred University. So I only applied to Alfred University. Unfortunately, they accepted me and I got to study glass there. And I remember when I first met Dr. Claire, I was a little bit sheepish because she was like a celebrity to me. And when I mustered up enough courage to talk to her, I found out she's actually a really nice person, really funny, very passionate about working with students. And the first time that I had a lecture about glass from her, I still remember the three most important properties of glass that she taught me. First of all, glass is strong. It is a very strong material. That's why it's used in so many applications that require high strength. Glass is also optically transparent, and glass is fun. Now, over the years as undergraduate students, we learned that even though glass is strong, if it has surface flaws in there, those surface flaws can compromise the strength. And so you can make glass weak if you have these surface flaws. And so it's not always strong. Also, glass is not always transparent. There are classes of glassy materials like metallic glasses, for example, that are optically opaque. And so there are exceptions to both of these first two properties, but no exception has ever been found to this third one. Glass is always fun. Now, from there, I went to work for Corning Incorporated. I actually worked in the glass industry for 18 years. This is Corning Sullivan Park Research Laboratory. It has about 2,500 employees up on a hill outside of Corning, New York. So I spent a long time there. I was working initially in a modeling and simulation department and then in the glass research department. It's just a really great intellectually charged environment with so many people with a shared love of glass and ceramics. When I started there, this was during the telecom boom, and I worked for several years in optical fiber and had a lot of fun with that. When the telecom crash happened, fortunately, Corning had flat panel displays up its sleeve, and this is what saved the company at that point in time. So I also spent many years working on the science and technology of glasses for flat panel displays. And then, most famously, on Gorilla Glass, the glass that is on over half of smartphones, and it's also on tablets and some touchscreen laptops as well. And that's really cool because one of the things about Gorilla Glass is that it helped to capture the public's imagination about glass as well, where I think it helped to change the public's perception of glass as being this old material that breaks easily to being a material that is at the cutting edge of science and technology and can be made to be very strong and very scratch resistant. Now, while I was at Corning, we were finding it more and more difficult to find well-qualified people to hire in glass science. It seemed like a lot of the professors that my colleagues and I had learned from were retiring, and they weren't necessarily being replaced by glass people. And so we did a study to look at the number of papers being published in scientific journals in the field of glass for different countries and over the years. And what you see here is that the US was on top for most of history. But the advances in glass in the US kind of stagnated around the mid 1990s. And it was a similar trend in Japan, which had been the number two country for a long time. They were actually declining in terms of their research output in glass. And Western European countries like Germany and France, they were also on the decline. Meanwhile, China had nothing going back to 1970, and they were investing heavily in many areas of science and technology, including glass science. And by 2013, they were about doubling the research output of the United States, and now they more than double the research output of the US. So they had made it a national priority. They had put their money where their mouths were, and they were getting results. And, meanwhile, we were stagnating here in the US. And we were really concerned about this at Corning, both for our own company in terms of, how are we going to find people to hire here in the US who are well trained, but also about the health of the US glass industry as a whole. And are we going to be able to compete long term with companies in China? And so we tried to do our best to make the case to the National Science Foundation and other government funding agencies about the importance of investing more in glass. We organized this Corning Glass Summit to bring together professors from around the country who are working in glass. We suggested over 100 specific research topics of things that we thought would be great for PhD projects, would also be great training for students. And, we tried to do our best. And then one day, um, I found out that Carlo Pantano, the glass professor here at Penn State, was retiring. And my now former boss at Corning told me I took the problem a little bit too seriously when I quit my job at Corning and came here to Penn State to be the next glass professor. So I've been here now for 9 years, and it has been a wonderful move. We've just found the perfect place really to do glass science and just a wonderful community at all levels, whether it's the department, the college, the university, the Happy Valley community. This young lady here, Sophia, she was 11 when we moved, and she is now a second year student at Penn State doing a triple degree. She's majoring in material science and engineering, English, and in music. We very quickly built the largest academic class group at Penn State. I made the case that there's a really strong demand for research in glass that is being unmet by the supply at US universities. and I turned out to be right. So I was able to very quickly, build up the largest program here in the country in glass science. And what was really satisfying for me is two of my PhD graduates actually became professors at my alma mater, Alfred University, and they organized a conference there a couple of summers ago called the University Conference on Glass. And I was able to bring a big chunk of my group back to my hometown of Alfred, New York, so they could see my hometown and attend a conference that was organized by a couple of my alumni. So currently, I've got three assistant research professors in my group here at Penn State. Dr. Hongyan Kim, who manages the modeling and simulation aspects of my research. Dr. Nick Clark, who actually started off as an undergrad in my group, did his PhD, postdoc, and now he's an assistant research professor. He manages line glass, which I'm going to talk about in the latter part of my talk, and Dr. Maziar Montazerian, who covers everything else in the group. So I've got a great team here, a wonderful group of PhD students. Alif, who's working on recycling and color compatibility of line glass. I'll show you a little bit of her research. Shaylee, who is working on polymer coatings on glass. Aaron, who does glass relaxation theory and is also a glass blower and is very passionate about STEAM education. Chong, who does MD simulations of crystal nucleation in glass. Christina, who works on dielectric glasses. Bahara, who works on zirconia glass ceramics. Dan Kramer, who actually works at Vitro in Pittsburgh and has come back to do his PhD working on line glass for float applications. Mason, who is co-advised by Song Kim in chemical engineering and who works on nucleation and crystallization. Mehmet, who does line glass for architecture and hollowware. Christian, who is working on fiberglass and glass refractory interactions. Jessica, who does fundamentals of glass corrosion. Ying Yang, who works in glass theory and modeling, and Donji, who's working on hollow glass microspheres. Also, several undergrads who bring a wonderful passion for not only learning about science, but having a positive impact. And so we're happy to have them in the group as well. We also just started a new Center for Glass Research. There was a previous Center for Glass Research that Carlo Pantano was one of the leaders of. This was between Penn State, Alfred University, and Missouri University of Science and Technology. That kind of disbanded about 20 years ago, and we decided with a new generation of professors at all three institutions and increasing demand from industry that this is the time to bring it back. So we've brought it back. Song Kim and myself are the co-directors. So Song he's the the day that I was appointed department head of material science and engineering, he was appointed department head of chemical engineering. So we are juggling our department head hats with also being co-directors of the center. Maziar is doing a lot of the heavy lifting here as managing director. Colin, my first PhD grad from Penn State, is the site director from Alfred University. Charmaine is a new professor at Missouri. She comes from a career at Pacific Northwest National Lab, and she's the site director at Missouri. Then Nick Smith, my colleague from Corning, he is chairing the Industrial Advisory Board, and Nick Clark is serving as industry liaison. We had our kickoff meeting last October. We had over 40 companies in attendance, from all around the world, basically all the major glass companies, a lot of small businesses as well, and also some of the consumers of the glass industry. So let me turn my attention now to our line glass project. The problem that we're trying to address here is the carbon footprint of the glass industry. Every year, the glass industry produces over 86 million tons of CO2 each year. About 70 to 80% of this is due to the energy consumption because of the high temperatures that are required for melting, and about 20 to 30% is due to the decomposition of carbonate batch materials. Now, as happy as I am with all the cool stuff we did at Corning, the fact remains that over 90% of the volume of glass that is made is what's called soda-lime silicate glass. This is the ancient glassing material that has not changed in a very long time. It's called soda lime because two of the primary ingredients are soda ash, which is sodium carbonate, and limestone, which is calcium carbonate. And when they melt, they decompose into oxides. They release carbon dioxide into the atmosphere. In the glass industry, it kind of put itself into this catch-22 situation where the companies that had enough profit to be able to invest in the type of game-changing technology that's needed to make an impact here, companies like Corning are just simply not interested in getting into the commodity glass space. And the commodity glass makers just don't have enough profit margin to be able to invest in this type of game-changing technology. So we found ourselves here at Penn State in a rather unique situation with me having my extensive background in industrial glasses, including commercialization of glasses, also having all the equipment here and students who are eager to make a difference. So we decided to try to take a stab at this problem, and what we came up with is what we're calling Lion Glass. It's called that because it's named after Penn State's mascot, the Nittany Lion. You'll see our Nittany Lion here on the shield in the lower left-hand corner. So that's where the name comes from, and plus all the best glasses are named after animals, as we know. What does Lion Glass do? This is a completely different family of glass chemistry. It's actually a phosphate-based glass instead of a silicate-based glass. It reduces the melting and the forming temperatures by about 400 degrees C. It also completely eliminates the use of carbonate batch materials. So this greatly reduces energy costs and carbon footprint. If you look at the table here at the top, this is the emissions that you get just from the batch to melt conversion process by melting 125-gram batch of soda lime. And you get 24.1 grams of CO2 that gets released. And the lower table here, this is for the same size batch for Lion Glass. All the carbonates are eliminated, and so the total amount of measured CO2 was zero point 0.3 milligrams. So it's just it's like atmospheric CO2, basically. Um, so that contribution to the carbon footprint is eliminated. The contribution from energy consumption is greatly reduced because of the significantly lower melting temperatures by about 400 degrees C. Another cool thing is that the strength of the glass, the retained strength after damage is quite a bit higher. So the upper right plot shows the probability of soda lime silicate glass cracking under a Vickers diamond indenter with increasing load. The crack initiation or the crack threshold is the 50% crossover here. So where you've got a 50-50 chance of popping in a crack. And in soda lime, that happens at 1 kilogram force. For Lion Glass, you can see at 1 kilogram force, there's a zero probability of cracking. And if you multiply that by 10, a 1 kilogram force, it's still just a 25% probability of cracking. So it has a much higher damage resistance. And this can either lead to products with better mechanical performance, or you can trade off that better mechanical performance to go to thinner walled products. And going to thinner products has multiple advantages because you're using less batch material, you require less energy for melting because you're melting less material. You've got higher throughput in the industrial manufacturing. And if they're lighter weight, that means all the downstream costs and carbon footprint is also better because the transportation costs are lower, the carbon footprint associated with transportation is lower. So there's a lot of benefits to going to lighter weight materials as well. And one final advantage of Lion Glass is that it shifts the UV absorption edge a little bit towards the visible. So it actually improves ultraviolet absorption. So if you're using the glasses packaging for anything that is sensitive to UV degradation, like cosmetics or some beverages, there can be some additional benefit there. One of the primary ways that this works is by lowering the viscosity curve. So the red and the orange here show a couple of soda lime viscosity curves. This is the logarithm of viscosity versus temperature. And in blue, this is Lion Glass. And you can see that the entire curve is shifted over to the left by quite a bit. This is, every part of industrial glass manufacturing is not really controlled by temperature. It's controlled by viscosity. It's controlled by how fast the molten glass is flowing. And every stage of industrial glass manufacturing is controlled by the glass flowing at a particular rate. And so in moving from soda lime to Lion Glass, what we want to do is maintain the same viscosities that are used now, but just shift the temperatures lower in order to match the same viscosities. This graph shows you some more details about the improved mechanical performance of Line glass on top compared to soda lime at the bottom. You can see the Vickers and denters here of soda lime at zero point 0.1 kilograms, zero point 0.5, and 1 kilograms force, and the cracks that pop in here with soda lime, and the cracks that are not popping in here with Line glass. What about thermal expansion coefficient? So the CTE is actually very similar between lime glass and soda lime silicate. So there's no difference in terms of the thermal shock performance. Another big trend in glass manufacturing is the move away from fossil fuels and towards electrically resistive glass melters. And if we working with our collaborators here at Aachen University in Germany, show that the electrical resistivity, which is it needs to be in a certain range to enable glass melting, that we're also in a good space there for electrical melting. What if you just look at Lion glass? Can you tell the difference just by looking at it? The refractive index profile is very similar between Lion glass and soda lime, so there's no difference there. The one thing that you might notice is that Lion glass is clearer. If you look at soda lime, it's got a little bit of a greenish tint to it, and that greenish tint comes from iron contamination. And with Lion glass, it's actually a lot more resistant to coloration. So it gives more of a pure perfectly clear color as opposed to this like greenish tint. Now, what I want to show you here is a graph. This actually is a video which is showing the batch to melt conversion process of soda lime silicate, where all the batch materials are here. So the soda ash, limestone, the quartz sand, and this is being ramped up in temperature. The current temperature in degrees C is shown in the upper left corner of the video. And so this is at 950 degrees C, and at 950 you can see these batch reactions are taking place. The minerals are reacting with each other. They're forming lower melting temperature eutectics. Gases are being released as the carbonates decompose into oxides. And see, this is ramping up to 1100 degrees C, faster and faster reaction kinetics. And the plot on the left here shows measurement of the gases that are being released during this process. You can see by far the most gases that are being released are CO2. This is the CO2 concentration divided by 100. So if you integrate this, you get 24.1 grams that are being released. The SO2 blisters are just because sodium sulfate is being used as a fining agent. So this helps to make larger bubbles so they can get out of the melt faster. And by the time you get to 1400 degrees C, you've got this kind of foaming behavior that starts. This is as the fining agent releases sulfate blisters. You get this foaming. And then as you get to 1500 degrees C, the foam calms down, the fining process is completing, and then you get to a nice homogeneous melt here that is bubble free. But it really does take those high temperatures in order to make this happen. Now let's compare this with line glass. This is the same experimental setup now with line glass, and you can see we're starting at lower temperatures. So this video here is at 650 degrees C. You can already see some of the reaction kinetics happening here at much lower temperatures. On the left, you can see the results from the gas chromatography, and you can see that the CO2 is now just in the noise. This is just basically either trace impurities of carbonates or atmospheric CO2. And if you integrate that, you just get zero point 0.3 milligrams. Instead of CO2, the main gas that gets released is water vapor. This is the water vapor concentration divided by 1,000. It is important to have gases that get released because that helps with the homogenization of the melt. And so what we're doing is we're trading in something that's environmentally harmful, CO2, for something that is environmentally neutral, H2O. This SO2 peak is just due to the fining agent, the same as in soda lime. Now, check out what's happening here. So we are at 875 degrees C. You've got really fast kinetics happening here. You've got these SO2 blisters coming through from the fining agents. 900 degrees C in line glass looks a lot like 1400 or 1450 in soda lime. And as we get to 950 degrees C, everything's calmed down. So 950 is a lot like 1500. You get a nice homogeneous melt here at about 500 degrees less in this particular case. This is Aaron. I mentioned that he's a glass blower. We have a glass blowing studio here on campus, and a lot of the properties that are required for glass blowing are the same properties that are required for being able to make glass bottles, for example. And Aaron is using line glass as an artistic medium to demonstrate its engineering properties as well. And so he's using our studio here to make this beautiful piece of art out of line glass. Um, we've got three industrial partnerships already with Line Glass. It's generated a lot of interest. Our first partner comes from Italy, Bormioli Luigi. They make high-end tableware and also cosmetics packaging. We are in the second year of partnership with them, and they've just indicated that they would like to continue with us going forward. And they are making glasses for cosmetics packaging. And I'm actually learning quite a bit about cosmetics that I never knew before. I never had the need to know. Chanel has told us explicitly that they would like the next generation of Chanel #5 to be packaged in line glass. So we are doing our best to make this possible. We had a pilot scale trial, actually a couple of pilot scale trials over in Italy. This first one took place in Murano, and that is very poetic for me because if you know anything about the history of glass, you know the importance of Venetian glass and the island of Murano. So, the medieval glassmakers, they kept on burning down Venice, and so they were forced onto this island off the coast of Venice, Murano, which is still the center of Venetian glass manufacturing and glass making. So if you go to Venice, make sure you go to Murano so you can check out all the cool glass stuff there. And this trial, you can see the side-by-side furnaces. The furnace on the right is soda lime. The furnace on the left is line glass. And you can see just what a lower temperature that we have with line glass. And this will show a movie. I don't know if this is going to work, but this will show a movie that shows some of, yeah, here we go, making the first line glass cup. So we're kind of ladling in the molten line glass into this mold. And the mold is being spun using a foot pedal. So there's a technician there with a foot pedal, and the faster he presses the pedal, the faster it spins around. And so the molten glass is being poured in there. As the mold spins faster, the glass is creeping up the sides due to the centrifugal force. As it's creeping up, the temperature is going down, the viscosity is going up, and so it's able to retain its shape. Now there's some cold air that's being blown onto it. You can see it's cooling down, and then this will slow down a bit as it continues to cool. And eventually, once he stops pressing the foot pedal, the mold is going to retract. So it's going to go into the plane of the table, and out will pop the very first line glass cup. And here it comes. Yay, there it is. And yeah, here's a close-up of it. We made a whole bunch of cups. So they've been sent out to samples to customers. We've got two other partnerships already in place. The one on the left here is Veralia. They are a French glass manufacturer, and they are interested in line glass for high-end spirits packaging. So we've been working with them, showing some really nice results. Interestingly, our lab is getting a reputation for having quite a bit of alcohol, but it's all for science, so no worries. Um, and on the right, Vitro. So Vitro, this actually, the U.S. headquarters is in Pittsburgh. This is the flat glass part of PPG, Pittsburgh Plate Glass, that was purchased by this Mexican company, Vitro. But we're working with their U.S. Based headquarters in Pittsburgh. And this is really cool for a number of reasons. One is, working with a Pittsburgh-based company is in line with Penn State's land grant mission to serve the Commonwealth of Pennsylvania. Um, Also, the student working on this is a former student of Carlo Pantano's who got his bachelor's and master's degree here at Penn State. Now Vitro's sending him back to get his PhD. And the other cool thing is that we're working on the float compatibility of line glass. So for architectural applications, so are we able to float molten line glass on top of molten tin in the same way that soda lime is done now, and make these really large sheets of glass for architectural applications? This is, the single biggest market for glass, and everything looks pretty promising right now. We've got another thrust that relates to the recycling of line glass. So, we want to make sure that it is environmentally friendly downstream as well. Line glass, like all glass, is in principle infinitely recyclable. The key thing is to be able to sort it from other types of glass. And so, one of my students is working together with the Pennsylvania Recycling Markets Center. So, this is at Penn State Harrisburg, and they've connected us with a lot of recycling facilities here. So my team went to visit recycling facilities around the tri-state area. And what we learned is that there is X-ray fluorescence equipment that is used to sort materials. And here's some of my team at these recycling centers. And right now it's used to, say, sort out lead silicate, so the so-called lead crystal, which is not crystal at all, it's glass. It's very important that lead not go into the cullet stream for soda lime manufacturing. And so right now XRF is used to detect the presence or absence of lead and sort it out. And the equipment that they use is from this Austrian company called Red Wave. So we actually have a partnership with for them as well, where we are developing the XRF standards, where they can update their software. And so the existing equipment with the appropriate software upgrade could be used to sort line glass and separate out the recycling streams between soda lime and line glass. So that is all in progress. And with that, I know you probably have some questions, so I'm going to stop here. I'm going to stop sharing, and I am happy to take any questions that you may have.
Thanks, John. That's just a wonderful presentation. I was struck by your first several slides, which showed, the fact that glass is ubiquitous in our
Mhm.
way of life. But
Yeah.
I think most people don't appreciate just how important and how prominent it is. So I wonder if you put those first maybe 10 slides that you
Mhm.
had together, you should there's some out there that should be distributed to the public so the public
Oh,
gets.
thanks, Ron.
I don't know how to do it, but I think
Yeah. Well,
just
hopefully we're making even a small impact here with this lecture and this recording that you're making.
yeah, yeah, yeah.
Yeah.
But I do have a more technical observation or question.
Mhm.
Lime glass is not soda ash and limestone. It doesn't contain carbonate. But what does it? What is its chemistry?
So it is a phosphate-based glass. It is a zinc aluminosilico phosphate. So
Uh-huh.
we are using basically phosphate minerals and zinc oxide, and in a way that it produces high quality, optically transparent, chemically corrosion resistant, mechanically strong, low viscosity melt. And these, batch materials are actually, they're not commonly used in the glass industry right now, but they are commonly used in the agriculture industry and of course zinc oxide in the sunscreen industry and
Uh-huh.
ceramics industry.
How did you come to that chemistry? What led you to that particular chemistry?
It's kind of just the basic principles of glass science, of understanding basic relationships between glass chemistry design and structure and properties, combined with honestly a lot of trial and error, a lot of failed attempts, and learning from each one. And after many failed attempts, we found ourselves in an area that seemed encouraging. We kept using feedback from each of our melts to inform the next steps that we would take, and after a while, we ended up in a place that was, very favorable in terms of its properties.
Where I'm heading with this is to ask, there's a project called the Materials Genome Initiative. It's
Hmm.
essentially computational material science
Yeah.
and engineering. And I just wonder whether, from your perspective, do you think right now we have optimized a CO2 free or CO2 limited
Hmm.
glass, or are there potentially other chemistries that may be even more appealing in that
Yeah.
sense?
Yeah. So, yeah, so line glass, it's a family of glasses, and we're continually exploring new spaces and trying to optimize within that family. The patent applications that we filed are actually fairly broad compositional ranges. It's
Yeah.
entirely possible that there are other compositional ranges out there that may be as good or better that are yet to be discovered. Is the materials genome approach the right way to do it? So I've done it this way before. I did this at Corning. I think we demonstrated actually before anyone in academia, the
Yeah.
successful application of the materials genome type of approach toward developing a new commercial product and doing it in half the time that it would normally take. I mean, we did that. We did that successfully, but we did that in a space where we already had a lot of data that could
Yeah.
inform us where we could construct these models. In the
Yeah.
case of line glass, it's such a totally new compositional space that the data just don't exist. And so that same type of materials genome approach really is not as useful in this type of space. So this is more like old school material science.
Okay. Just one final question before I turn to the
Mhm.
hands that are up. I'm
Yes.
very fond of beer. Are there beer mugs made of wine glass? I'd love to have one.
Not yet, but in the
Not yet.
future. So we're
Oh,
starting
darn.
off in kind of the high-end spirits
Yeah.
industry because the markup is quite a bit higher, so they can afford to invest some more in the engineering that's required to scale
Okay.
this up. And also the volume is smaller, so it's kind of a better way, a better entry point into the market. And once it gets established there, then my hope is it'll go out into more of the consumer wines and beer industry. But yeah.
Wonderful. I'm looking forward to it, John. Thank you.
Great.
Let's turn to the hands. Eddie, you're first.
Well, it's funny you mentioned the Murano glassworks because my father knew the people very well. He was a tour manager and he got a lot of the got a he had a good relationship with them. In fact, my family actually has several sets of Murano glassware of
Wow.
gold and bold, embossed glasses and beautiful colors and what have you.
Mhm.
Um, I, so one of my questions, Ron actually asked quite a few of the questions I
Mhm.
was going to ask.
Yeah.
But one of my questions was their reaction to Lion Glass? Did they find, I mean, they blend it in with all kinds of chemicals to give the gorgeous, beautiful, you know, hues and colors
Oh
and so
yeah,
forth.
yeah,
Is
yeah.
that I was just wondering if Lion glass is exactly the same as the old glass, and did they have any
So
comments about it?
yeah, line glass can also be used to color glasses. So here's blue line glass. So this is colored with copper. Here's some pink line glass, which is colored with erbium. Um, so what else? This is if you put enough iron in it, you can make it dark green and black. Here's some blue line glass that's made with
Huh.
cobalt. So all the same transition metal and rare earth dopants that you use in soda lime, you can use them all with line glass too, and you'll get a very similar type of coloration. The difference is the concentration of the dopant that you need, and so that the concentration may be different in going from soda lime to line glass.
My last quick question is there any supply problem with the type of material
So the
that you need for it?
yeah, you mean in terms of colorants?
Not in calories, but the actual material itself. Is there any issues with that? I mean, is there a problem, for example, where you get your supplies from? Is there a specific rock that you need? It might be somewhere in Italy
Oh
or
no,
somewhere,
no. So the
or is it
supply
just
streams are
generic?
set up for all the raw materials that are needed. They're just not like connected to the glass industry at this point. So it's more, these materials are used in other industries and we're kind of tapping into that for glass manufacturing.
No problem with supplies.
Yeah. Yeah.
Michael.
You've answered some of my questions during the process. CTE, I would assume that it's around 86 or so. Therefore, you don't have the heat resistance of a borosilicate. Is that a correct assumption?
That is correct. Yes, it's more of the
Oh,
soda lime thermal shock resistance, not borosilicate thermal shock resistance.
okay.
Yep.
And if can you temper it? Can you temper plates?
Yes, yes, you can temper it. And actually, the lime glass there are a couple of reasons why it is better than soda lime for thermal shock resistance. One is that it takes more stress in order to pop in cracks. and the other is that it has a lower strain point. And so if you look at the kind of the upper limit of the integral for where you're generating stresses, it starts
Mhm.
with a lower upper limit. And so the integrated stresses are actually lower, even though the CTE is about the same. So there are some advantages, but it's not as good as borosilicate
Uh-huh.
for
So,
thermal shock resistance.
thank you. So then in that case, could you, what's the heating te in the tempering process? What's the heating temperature and how cool do you have to get it? How quickly?
So it's the same process as for soda lime. You match the viscosities that are used for soda lime and just shift the temperatures down so that you get equivalent viscosities.
So you save CO2 output in the tempering process as well.
Correct.
Very
Yes.
interesting.
Yeah.
And let's see. Okay, and so I guess those are my. This is what we were doing with glass for a while. And we were
Oh, nice.
engraving images into plates of glass after
Uh-huh.
coating the background. We wanted to start with a low energy flat plate
Mhm.
light source, but there was no market for it. So
Mhm.
then we started engraving
Yeah.
images into plates of glass, and this was
Okay.
called plate glass neon, and it was very interesting we built quite a market around that.
Very
It's a
nice.
very, very interesting presentation, really amazing. Thank you so
Well,
much.
thank you, Michael.
Let's see, Jenny.
Okay. Well, thanks for the presentation. I really enjoyed that. I have two questions. First is I'd like to see your comments about alkali-free
Mhm.
glass. You know, how's the potential,
Mhm.
and then related to that is the second question. That is in another industry sector in terms of application is quite of interest in replacing the silicon in the semiconductor chip packaging area because the intrinsic property superiority of the glass
Mhm.
properties to the silicon and certainly organic substrate as well. And so a lot of interest in that area. I just like to see what's your view about that as well.
Absolutely. Yeah, there is a lot and growing interest in glasses for semiconductor packaging. I think there's a lot of room for innovation because, as you've implied, alkalis are kind of the enemy here when it comes to dielectric loss. And moving from an alkali containing glass to an alkali-free glass can lower the dielectric loss quite a bit, which is beneficial for electronics packaging. So alkaline earth based glasses, like the glasses that are used for flat panel displays, offer markedly improved performance compared to traditional alkali-containing glasses. And what would be even better is if you remove all the modifiers. So if you remove all the alkalis and the alkaline earths and just have pure network formers, that would give you, even better performance.
Okay, thank you.
Thank you.
Albert. You're muted, Albert. Yeah. Okay. There you go.
Very, very nice presentation. And in the beginning, these multiple application you showed, as I was looking at them, I said, many of them I could do with plastics.
Mhm.
And my question to you is, from an energy and a clean climate perspective, climate warning, etc., are we better off with glass or plastics when you could satisfy the need with either?
Great question. So, yeah, pros and cons here. So, for the glass, you're using much more abundantly available natural minerals. So, from the raw materials, the glass would have an advantage. When it comes to energy consumption for actually doing melting and forming processes, plastics have the advantage because they would be using lower temperatures. When it comes to recyclability, glasses in principle could be recycled infinitely, whereas with plastics, there'd be more degradation over time. I think overall, even though a lot of these products they were initially made with glass, some of them have sort of migrated to plastics for various reasons, either lower in cost or the higher fracture toughness, so that they're more resistant to breakage from dropping, for example. But I think we are going to see more trends of moving away from plastics and back to glasses because of the net benefits that glass can offer from an environmental viewpoint. And I'm hoping that with the move from soda lime to line glass, that can help to accelerate the move back, from plastics to glasses.
Sounds good. Of course, if there were a plastic person here, they may
Yeah,
have
they
a
may
different
argue
opinion,
against
but
me.
that's all right. Just a few minor thoughts.
Uh-huh.
The one glass that was done in Morono was not very clear.
Mhm.
Why is
So it,
that?
it it had it had some inclusions in it. We hadn't yet optimized the melting process, so there were some inclusions that we needed to take back to our lab, and that's all been worked out since then.
Okay, and I noticed in your first early comparison of emission per pound of material, the SO2 doubled with lime glass versus soda glass.
Yep.
Is that a
So the
concern?
SO2, that actually doesn't matter. That's just an additive because of the sodium sulfate, which is used as a fining agent. We were just trying to use an equivalent amount of sodium sulfate in both cases for an apples to apples comparison. What we found is that line glass doesn't actually need a fining agent, so there's no need to include sulfate. So it's pretty easy to zero that out.
Okay, that's good. Last comment is more of kind of a fun comment regarding Murano. Um, I was for a whole week in Venice,
Uh-huh.
and at the end of the week, I was surprised that the Italians didn't try to rip me off in anything. Then the owner of Vaporetto offered to give me a free lift to Murano to see the glass, so I went with him. Then when I asked for the Vaporetto to take me back, he said, "No, you didn't buy. You got to pay to go back." I thought that was kind of an interesting thing, but it's a warning when you go to visit Murano glass.
All right.
That's the story.
Remember
Thank you.
that.
I will say I didn't have that experience, and I found the Moroccan people very nice.
And you didn't
My
buy
family.
either.
Well, actually, I already had about, I mean, my whole family has sets and sets of the glassware, which we've got when we got married or had babies or whatever. So we've got the crystal clear glass and we've got the whole, wine sets and God knows what.
Yeah.
Well, thanks, Albert. I appreciate that. Good question. Before we move on to Avi, John, I just want to ask a corollary to Albert's question. I got these glasses within, I don't know, past several months. They had plastic lenses.
Yeah, yeah.
I could not find glass lenses anywhere. What happened to what's the story there?
So it's lower cost, and if you drop them, they're less likely to fracture. They're a lot more likely to scratch, of course, as polycarbonates.
Yeah.
But yeah, in the US, it's basically moved to all polycarbonates. If you go to Europe, you should be able to buy either in Europe. So if you wanted to get glass spectacles, Europe is the place to go.
Yeah. Well, what's the motivation though? I mean, why did the US make that change?
I think it is mostly a cost savings
Oh, I see.
effort.
Okay.
Yeah. Yeah. But
Yeah.
it is annoying because they do, they scratch up a lot more easily compared to
Yeah.
glass.
Yeah. Okay. Let's
Yeah.
go on to Avi.
What is what's the frequency range of transparency? You mentioned something about ultraviolet, but what frequencies will lion glass allow to go through? Is it different from soda lime?
It's very similar to soda lime, but the UV absorption edge is just shifted a little bit closer to the visible. Uh, hold
And
on,
where
let
does it
me.
become opaque?
Oh, okay. Let me try to find. I gotta look up the curve, so I don't have the numbers off the top of my head. Um, hold on.
I mean, when you say the UV is shifted to opaque, or
It's
rather to
shifted
the visible,
towards the visible. Yeah, so
then it's
the
not UV
absorption
anymore. It's the
edge.
visible. Then it's the visible wavelength that we're talking about, isn't it?
So it's transparent across all of the visible. Um, I gotta look up my own paper. Um,
Meaning it's not transparent in the UV, basically. Is that what you're saying?
correct. It's not transparent in the UV. It's opaque in the UV. It's transparent in the visible.
Is it transparent in infrared?
Uh, just a little ways into the near infrared.
Because it's still a problem. It's in the car. You don't get a sunburn, but you get hot with
Yeah,
the sun coming.
exactly. It's not going to do anything for that
Is there
problem.
just a single band of transparency, namely in the visible
Yes.
electromagnetic part of
Yeah.
it?
Yeah.
On either side, it's opaque.
Correct.
I just found myself wondering if there would be any value in having a glass that would be transparent in other frequency ranges, maybe even and opaque in the visible range. I don't have any place. I'm not going anywhere with this. Just occurred to me that there might be some uses where the glass would, in effect, filter out all but a certain frequency range, other than visible, that might be useful in some applications. And I just wonder
Yeah. Yeah.
how Lion glass.
Yeah. Um, that could be. I think you would probably need some more dopants to control the window exactly. And if you want to go to just very narrow bands, making it into some sort of gratings would be helpful. And of course, there's other families of glasses too that are opaque in the visible but transparent in, say, the infrared, chalcogenide based glasses. And, yeah.
All
All
right.
right.
All right. Let's go. Michael, you have your hand up.
Yeah, I just forgot to ask one more question, but let me make a comment too on the transition from eyeglasses to plastics. Due to the change in the refractivity index, you can make a thinner glass out of plastics than you can out of glass. So the Coke bottle effect on certain prescriptions is less with plastic than it is with glass. The other question, I was really impressed that you pointed out that similar in my world of Rockwell test is when you put a point source onto a metal to test its hardness. And in your case, you were pointing out that that same type of a test, I forgot what it was called, if you put a tenth of a kilo onto a regular soda lime, you can put a kilo onto Lion glass and it'll survive. But let me ask, does that mean that the internal stress, which I understand is about 1,000 psi, if you apply a heat source, does the internal stress required to induce a crack increase also
So
10
yeah,
times?
that's basically what's going on literally under the surface is exactly that. So the glass itself has other mechanisms for relieving the localized stresses. Basically, and honestly, this is the same trick we played with Gorilla Glass, starting with Gorilla Glass 3, is that we're introducing plastic deformation mode within the glass structure, kind of at the nanoscale. And so it's able to absorb that energy in a more productive fashion than by introducing a crack.
Well, that's incredible. Thank you so much.
Oh,
God, I
thank
really enjoy
you.
your work.
Thank you.
All right, let's go to Pete. Thanks, Michael. Pete?
Yeah, very good presentation. I hear all the good stuff. What are the downsides on lying glass? What are the limitations?
Well, the batch materials are more expensive compared to soda lime, and there's no way to get around that because soda lime uses some of the most abundant minerals available on Earth. So there's a trade-off in that the raw materials are more expensive, but the energy costs are lower. So from an economic point of view, you can have scenarios where lying glass is either more expensive or less expensive, depending upon the relative batch material costs versus energy costs. And so there's a geography dependence there. And then it's just
In
it's a
application?
change. It's oh for applications.
Yeah.
It's suitable for wherever soda lime silicate is used. It's not a replacement for borosilicate. It's not a replacement for Gorilla Glass. It's a replacement for one thing for soda lime, but that one thing is used in so many different products.
Okay. Thank you.
Yeah.
80.
Yes, I'm just wondering, it sounds like there's some restrictions in terms of the spectral characteristics. Now, does that, for example, impact things like WDM if you're going to try and use it for fiber optics,
Oh, yeah, you would
that
not
kind of stuff?
yeah, don't use this for optical transmission. So it's I mean you need to have water-free glass
Right.
for telecom. So fused silica is the way to go. This is not a replacement for that.
Thank you.
Yeah.
Bob, you're going to have the last word today. We're approaching the 12 o'clock break time, and I want to let our guest get back to his problems at the university, but let's go to Bob. Bob, you're muted. Yeah, there you
Thank
go.
you for a terrific presentation. Most enjoyable, very thorough. Uh, my special focus at the moment is thinking about high performance lenses for optical lenses for photography. And is there a significant difference in density and refractive index compared to current materials that would give us lighter
So
lenses?
are you specifically using high refractive index lenses?
Uh, Frankly, I don't know the optical
Okay.
formulas in Nikon or
Okay.
Canon
So
telecom.
yeah, so thank you. The optical properties are more similar to just standard soda lime silicate glass. If you're using specialty glasses, like specialty optical glasses that have higher refractive indices,
Mhm.
then this is not a replacement for that.
Okay, thank you.
Yeah, thank you.
So actually, I lied. Avi is going to have the final question today. Go ahead, Avi.
Uh, well, I was just wondering, what you're doing with regard, is there a next generation? I don't know what the animal would be, but is there, a panther glass or something that would be the next generation beyond lion glass?
So we have kind of multiple generations of line glass under the hood here. We've got a series of patent applications that represent generational advancements within this family of what we're calling line glass. So we're still using that moniker at least for now.
I was going to
But
say, what's the next mascot that,
yeah, my uncle wants me to make an armadillo glass, but
that's it.
I'll save that for later.
You could continue with the lion glass tradition and call it paterno glass or,
Yes.
something like that.
Yeah, I can
Uh,
ask Sue Paterno for permission.
John, I want to thank you for joining us today. It's been a wonderful presentation, and you can tell from the Q&A that we had lots of interest. I I, uh, I want to thank you for being with us today, and we'll look forward to watching the evolution of lion glass in many other ways, I'm sure, into our economy.
Oh, thanks
Uh,
so much, everyone.
We'll meet again in 2 weeks, folks. We're gonna have one of the world's foremost orthopedic surgeons speak to us. He's at Rush Presbyterian Hospital, a guy named Josh Jacobs. Turns out to be one of my former students. You're getting lots of applause here too, John. So he'll be speaking with us. I can see the applause floating up on the screen. But once again, we'll take a break at this point. Have a good weekend, everyone. Thanks again, John. See you
Thank
next
Thank
you.
week.
you. Yeah, bye bye.
Bye-bye.
Yeah.
Bye-bye.